So from last video, we introduced this definition of matrix coefficient. So basically, for each irreducible representation, we define a bunch of continuous functions from G to the complex. And they are some finite dimensional space. And we saw that if you have two things that are unitarily equivalent, then these matrix coefficient, they will span the same space. And also, these spaces are invariant under the left regular representation. And we're going to now introduce the next step. So we're going to talk about this theorem called Schur's orthogonality. Basically, it shows the following. So if you consider two representations, if they're not unitarily equivalent, then they're actually orthogonal to each other as a subspace in the L2 of G. So this orthogonality is really understood inside the Hilbert space L2 of G. So you take their L2 inner product, they always give you zero. So you can think about this is kind of a way to decompose your L2 of G into a bunch of finite dimensional subspaces. Okay, so this is the first step. And second, we also want to describe for each of these e pi. So want to describe its orthonormal basis. As it turns out, if you just consider the kind of the basic matrix coefficient, so these pi ij. Of course, you need to multiply by some scalar. You need to scale it by the square root of b pi. They're in fact an orthonormal basis for these e pi. So not only we know these e pi are finite dimensional invariant subspace for your left regular representation, the second part basically tells you its dimension is just d pi squared. Okay, so this is quite important and technical lemma. So let's give a proof. So the proof, the idea is actually quite neat. The two ideas are kind of similar. So for the first one, so let's just consider if I have a, say, UV inside the H of the first one, H pi, and then I have two other things, let's say W and Z inside the pi prime, the H of pi prime. Then I just need to evaluate their L2 inner product. So let's do the following. So let's put the complex conjugate to the first one. So technically I should put it on the second one, but it doesn't really matter. I just need one. All right, so I put the phi of pi, and then I have phi of pi prime, and then I have W and Z, evaluate x and dx. All right, so what it does is essentially the following. So I have the first one is an inner product. I have a V first, and then I have a pi xu. And then on the second one, I have this pi x, pi prime of x evaluate and W. Then I have a Z in the product, and then we have a dx, all right? So one way of thinking about these products of inner product is using the following trick. So the idea is, let me write it on the side note. So here, if you think about the inner product with A and B, so let's say A and B, they're just column vectors. So this is basically, you think about it as the A star, you kind of transpose your A as a row vector and you multiply by B. Okay, so you think about it as A star B. And then you multiply C and D, so this is also C star D. So what you end up with is A star B times the C star D. That's the product of these two inner product. But another way of looking at it is that you have a BC star. You just try to break it here. So what BC star does is basically kind of the following. It looks like, so B is a column vector, and you multiply a C star, which is a row vector. So it looks like a n by n matrix. This is essentially just the rank-1 operator. So this BC star evaluate at a vector is essentially you let C do the inner product with B. So this is V and C. And then you multiply by B. Okay, so you end up with this rank-1 operator. So this is this two product of this inner product looks like a rank-1 operator applied on D, and then you inner product with A. So that's kind of the idea. I know I might have messed up with a star or something, but the idea is that if you write it like that, so let's just use this notation. So you end up with a V star in the front. Inner product with this rank-1 operator, so you have this pi x u times the pi prime x, let's just write pi prime x w, the whole thing star, and then you have inner product applied to z. Okay, and you can do the following. So let's have pi x u, and then you have a w star, you have a pi prime of x, and then you have a z dx. The point is this uw star is a rank 1 operator, and then you multiply the pi x and pi prime of x, they're just n by n matrices, and then you can regroup them. So this is, you can check. This is essentially just the integral, or you think about, you move the integral inside. So you think about it as the vector v taken the inner product with the integral of these pi x times these rank 1 operator uw star times the pi prime of x dx. Okay, so that's going to give you an operator. And then you have this, I should have an inverse here because I have a star. Okay, and then you apply this whole operator to z. Okay, so if you recall what we did a few lectures ago, so if you have a, let's say b is this rank 1 operator uw star, so essentially b times vector is just this vector inner product with w, and you apply the scalar multiplies to u. All right, so and this a now is essentially just the integral of the pi x times b times the pi of x inverse, or pi prime of x inverse dx. We saw that this operator is going to intertwine these two representations. So this is in the intertwiner of pi and pi prime. And so because of pi and pi prime, if they're not unitarily equivalent, we have a Schur's lemma that tells you, well, there's not many intertwiners, there's only 0 in there. So the C of pi prime only contains 0. So this is going to be equals to A. So basically that tells you A is going to be equal to 0. So because A is equal to 0, so this whole integral is going to equal to 0. Okay, so this one is going to 0. So in other words, these phi of uv is going to be orthogonal to this phi of w z with pi prime. Okay, so that proves the first part of this theorem. Okay, so if you have two representations, if they're not unitarily equivalent, then their matrix coefficients are orthogonal to each other. Okay. All right, so now let's think about what happens if they're not orthogonal. Okay, so let's just fix some orthonormal basis. Let's say E1 up to E of d pi is an orthonormal basis for the h pi. And let's think about what happens to their matrix coefficient. So if you think about, if you do the inner product of these matrix coefficient, basically let's just write this out. So if I consider pi ij, so pi ij is the pi x inner product with the e, let's just use ei and ej. This is technically pi ji. You do the conjugate, and then you do the pi x of ek with el, okay? And then this one, so basically use the same trick, okay? So this is going to become a big inner product where you put the ej first, and then you do the integral of this, not summation, integral of this big operator. You have the pi x on one side, and then you have a rank 1 projection, this ei ek star, basically taking the product with ek and then multiply on ei. And then you have the pi x conjugate, pi x inverse. This whole operator applied to this el, okay? And so basically you do the same trick. You let this is equal to b, and this big integral is going to be equals to a, and by the technical lemma we saw, this is going to be in the intertwiner of the pi itself. And again, by Schur's lemma, we know this because pi is irreducible, this is going to be equals to lambda times some identity. Okay, so we know that this a is going to be equals to lambda times the identity for some constant. Okay, so the thing is, we just need to now find this lambda. Okay, so what is this lambda? And this can be done by a very nice trick. So if I consider the trace of this matrix A, well, the trace is essentially sum of the diagonal entries, and lambda I, basically you have it's a d pi by d pi matrix. You have lambda on the diagonal, so the trace is fairly easy to compute. But on the other hand, this is essentially the summation of the, let's say I going from 1 to d pi of you take your matrix A and then you inner product with the the, let's maybe change another letter, let's maybe use M. So you do the inner product with the M's orthonormal basis, and then you inner product with itself. So this is kind of give you the diagonal entry on the M entry on the diagonal, and then you sum it up. Okay, so what it does is, let's just write by definition. So this is going to be equals to integral. I'm going from 1 to d pi. You do the integral. So A is an integral. You move the integral inside the inner product. So this is integral of the pi x. You have the rank 1 operator, let's call it B. And then you have the pi x inverse. And then you have the En inner product with En dx, okay? So now you can do the following trick. So let's move the pi x to the other side. Okay, so I still have the summation. I'm going from 1 to d pi. I have an integral of b applied to this vector, pi x inverse or pi x star applied on En. And inner product with the pi x star on En again. And this whole thing dx. And you can move the summation inside the integral, of course. So let's just move the integral outside. Okay, so let's do the integral of this whole thing. But if you fix an x, so because your pi is going to be a unitary representation, so your pi x of this ei, so I going from 1 to d pi, and that's also a orthonormal basis. Okay, orthonormal basis. It's maybe a different one, but it's still an orthonormal basis. And the formula for the trace doesn't really care which orthonormal basis you pick. Okay, you can say let's take A inner product with EM and EM, or some Fi with Fi. Okay, as long as you're taking an orthonormal basis, you do the inner product, you sum up the diagonal entries, then you get the same trace. Okay, so all of these summations are going to equals to the trace of B, because you're basically testing it against this new orthonormal basis. Okay, so this is going to be equals to the trace of B. Okay, so this is the whole thing is just integral of the trace of B dx. And of course, you normalize your integral on the whole group to be equals to be a probability measure. So this is just end up with the trace of B. Okay. So what you have is the following. So let me just write down what do we prove. So we know the trace of A, which is equals to lambda times d pi. That's equals to the trace of B. But what is B? Well, B is this rank 1 operator. So B is, if we go back, okay, so let me use the red circle. So this is B. So this is the thing that takes EK to EI, okay? Where you think about this is just the matrix where there's only one entry that's going to be equals 1. That's just going to be the ikth entry, okay? So this is EI, EK star, and you can think about it as, if you think about it as an n by n matrix, it's just a bunch of 0, and then there's only one entry which is equal to 1, and that corresponds to the ikth entry, okay? And this trace, you see, this is most of the time that's going to be equal to 0, okay? So this trace of this A is just going to be equal to 0 if I is not equal to K. If it's not on the diagonal, of course, you get trace of B is equal to 0. But if it's on the diagonal, okay, so then what you have is that you end up with A just equals to 1 over d pi, okay? So that's if I is equals to K, okay? So basically what we have is that we are considering, we plug in this back to our formula. So if I take the inner product with pi ij with pi of KL, okay, a lot of time that's going to be equal to 0. So if I is not equals to K, that's going to be equal to 0 because A is going to be equal to 0. But if I is equal to K, then what we end up with is the following. So A is going to be equals to 1 over d pi times the identity, but what we're testing it against two vectors again. Okay, so I'm testing against EJ, and then I apply the right hand side to EL, and this inner product again is going to be equal to 0 if J is not equal to L. Okay, so overall we have that this is essentially, if I just use the chronicle delta, so if I and K are different, then we're 0, otherwise it's 1. And then if J and L are different, okay, then it's again a 0. But if they're all the same, then what we have is this constant 1 over d pi, okay? So as you can see, their inner product is going to be mostly 0 unless this ij and kl corresponds to the same entry. All right, because they're inner product, you have this d pi. So apparently, if you multiply the square root of d pi, their inner product now becomes 1, and then it's also normal basis. So we have that square root of d pi, this pi ij, that's going to be is an orthonormal set. Okay, they're orthogonal to each other. And because we saw the dimension of this e pi is, well, this e pi is clearly spanned by these pi ij, and because they're orthonormal, so they have to be orthonormal basis. Okay, so it's orthonormal basis for this e pi. Okay, so that's what we want.